Welcome back guys. Today we'll be learning about calculus of functions of several variables. Today we'll be learning about maxima and minima. So let z equals to f of xy be a function of two variables. A point of x0 y0 is called maxima of f of xy if f of xy is less than f of x0 y0. So this is for the condition of maxima, and for minima it will be f of xy must be greater than f of x0 y0. So this was for maxima and this was for minima. So this is just the basic definition for maxima or minima. So there are some theorems on maxima and minima. So theorem number 1 is, so for the function z equals to f of xy will be has a maxima or minima at x0 or y0 when then del of f or from del of x at the point x0 y0 will be equals to 0, and del of f upon del of y at x0 y0 will also be 0. So for maxima or minima, del of f upon del of x at x0 y0 and del of f from del of y at x0 y0 will be 0. So our theorem 2, or the conditions for extrema, that is maxima or minima, extrema. So suppose for z equals to f of xy, so first or this condition is satisfied at if, suppose if AB is the point satisfying the equation that is del of f upon del of x equals to 0 and del of f upon del of y equals to 0. So now a function h is defined as h of x comma y, that will be equals to derivative f of xx of xy times f of yy x of y minus of f of x then y x of y whole square. So this is our function h which is defined. Now for this function we have some conditions. So our condition number one is if AB is the maximum point, AB is maxima point, then if only if when h of AB, means putting the value of h AB here, that must turn out greater than 0, and also the other condition is f of xx putting value AB must be less than 0, or for f of yy AB must also be less than 0. So you need to check only one, both these conditions should be checked, this or this, either this or this. So that was for maxima. For minima it will be AB minima, that will be h of AB must be greater than 0, and f of xx AB must be greater than 0, and similarly for y or for y f of yy AB must be greater than 0. Now if AB is neither a maxima or minima at the point, so only when if h of AB is less than 0. For less than 0 it is neither a maxima nor a minima, and for AB and suppose if h of AB turns out to be 0, then no inference can be developed or concluded. So these were some theorems. So we have also another theorem, theorem 3. So that is basically an alternate condition or alternate theorem for z that is equals to f of xy if df, that is at a point AB, then AB is called maxima if D2F is less than 0, and for maxima, for minima, D2F must be greater than 0, and nothing can be said when D2F is equals to 0 for no inference. These all are for function at AB. So these were the theorems. There are some other definitions that you need to remember, that is saddle point. Saddle point. So a point is said to be, a point suppose that is A of B is said to be a saddle point only when a saddle point of function that is z f of xy if f of xy has neither a maxima nor a minima, at a comma b. Although if f of x ab, that might be equals to ab 0. So a point is said to be saddle point if it is neither a maxima nor a minima. So now another definition is critical point. So critical point, a point that is AB is said to be a critical point of function f of z of xy. A point of AB is said to be a critical point of function only when f of x AB, first derivative and first derivative with respect to y, both are 0. So these were some base definitions of maxima minima.